Okay, we're going to continue on here in chapter 10. So we started talking about acids and bases last time there. So acids and bases, remember, acids are things that have the ability basically to produce H plus ions in solution, or again, H3O plus, which is pretty much the equivalent there. While bases are guys that can produce hydroxide ions in solution. And sort of a general definition of acids and bases, or one that people use a lot, is the Bronsted-Lowry definition. And in the Bronsted-Lowry definition, an acid is a proton donor, so something that gives away an H plus. And a base is a proton acceptor, which will accept the H plus. Remember that this creates sort of a pair situation that occurs when you have acid and bases here. It creates a conjugate acid and a conjugate base on the other side, where the acid is related to the conjugate base and the base is related to the conjugate acid. Remember that the difference really is only one H plus. So it is the H plus that's being donated over there from the acid to the base. And that should be the really only difference between those two. If you were asked, are they pairs or are they not pairs? The acid would have one less H plus, or the conjugate base would have one less H plus than the acid. And the conjugate acid would have one more H plus than the base in that case. Remember that acid and bases, just regular acid and bases, are only found on the left-hand side of the arrow. All the conjugate partners are found on the right-hand side of the arrow. And again, if you're sort of asked, to write either the conjugate acid or conjugate base, I think we looked at something like this guy here last time, which is bicarbonate. And if you wanted to write the conjugate acid, all you have to do is sort of remember that the conjugate acid is what I'm looking for, which means what I am looking at is a base. And that means that the base should accept the H plus. So we would put the H plus onto this, and it would be H2CO3. Remember, when we put the H, we gain the H, but that plus is also important in terms of the overall charge. So +1 and -1 gets us to 0. While if we were looking at something like the conjugate base in this case, we were looking for the conjugate base, its partner would come back this way to the acid, which means the acid should donate the H plus. And when we take the H plus off, that is CO3 2-, which is carbonate in this case. This is, as we talked about, something that could act as an acid or a base, and that is what is known as an amphoteric substance. Typically, things that have a hydrogen and like a negative charge have the ability to kind of go both ways, either give away an H or accept an H. Obviously, things that don't have an H can't give one away, so they can never be really an acid. So sometimes those guys with the H and the minus charge can do both. Water is also another thing that is an amphoteric substance. It has the H. It could actually give away an H in certain cases. It actually accept the H in other cases. And as we talked about last time, what happens when we do get water sort of reacting with water is it creates an equilibrium with H plus and OH minus, and it creates a relationship which is known as Kw. And Kw is the equilibrium constant for water, and it is the concentration of H plus times the concentration of OH minus. And this is usually molarity. When we see that concentration, that is molarity. We also can substitute out, as we talked about, H3O plus in any sort of formula as well. So it is the same thing. And that would equal 1 times 10 to the minus 14. So what we could use this for is to figure out, is the acid part of the solution more than the base part of the solution? So we could solve for the H plus concentration by taking 1 times 10 to the minus 14 divided by the OH minus concentration, or we could do the opposite. It is really the same calculation, regardless of which one you're looking for. We also talked about the importance, obviously, of using our exponent button. So you definitely want to make sure you're using your exponent button when you punch these guys in to do so. In that case, what we would do is compare the H plus concentration to the OH minus concentration. And if it is larger, then it is going to be an acidic solution. If the H plus concentration is less than the OH minus concentration, then it will be basic. And if they are equal to each other, then it will be neutral in that case. Also, as we talked about, when you are comparing those concentrations, remember that the negative that you have in those exponents when you do the concentrations are important. So again, the smaller negative exponent is actually the larger number. Again, the negative exponent means you're going to go to the left, put a bunch of zeros. So the smaller number you have there actually is the larger number. Any questions on any of those things we talked about there? Yeah. All right, then continuing on here. Let's do this one. Let's forget about what it's actually asking. Let's calculate the OH minus concentration here. And is it acidic, basic, or neutral? Okay, let's take a look. So again, in this situation, we will definitely be using KW, which is something that you always have. Again, may not be given to you or something like that. But once again, for our purposes, this number is pretty much a constant. So you always have sort of that relationship that you could use. And as I mentioned before, it really doesn't matter sort of which one they give you. It is really the same calculation no matter which one they give. So here the OH minus concentration would equal our KW value, which is 1 times 10 to the minus 14, divided by our H plus, which would give us 1 times 10 to the minus 14 divided by 2.8 times 10 to the minus 5. Once again, we're going to do a 1 exponent button, right? Negative button and 14. Divide 2.8 exponent button, negative button, and 5, and then equals button. Yeah. So again, that is the proper way to punch that in. And if you do that, let's see here, negative 5, you end up with 3.6 times 10 to the minus 10, and it would be molar as it is a concentration in this case. Any questions on that one there? That means that this would be acidic, basic, or neutral in this case. So once again, really all you have to do is look at this last part of each of these. So the H plus is to the minus 5. The OH minus is to the minus 10. So to the minus 5 is a much larger number. So in this case, the H plus concentration is greater than the OH minus concentration, which means this guy should be acidic. Any questions on that? So again, a reminder just to visually show you, if we turned our H plus concentration into a decimal, it would be 0.1233428 molar. We did our OH minus in a decimal form, it would be so this is a much, much smaller number. So again, that negative part of the exponent is really, really important there. Yeah. Any questions on that one there? All right, so let's try this one here. Don't worry about this. Let's just do our OH minus cost. Okay, so once again, as we've talked about, we're going to use KW, which it is going to be pretty much the same calculation as previously. 1 times 10 to the minus 14 divided by our H plus concentration, which is 1 times 10 to the minus 9 in this case. Again, making sure you use your exponent buttons on both of those numbers will give us 1 times 10 to the minus 5 molar in this case. In this case, once again, we are looking at the OH minus versus the H plus concentration. And in this case, it is actually the H plus concentration that is less than the OH minus. Again, to the -5 is a larger number than to the -9. And that means that really the basic part here is larger than the acidic part, which would be that part. So it would be basic. So remember that really the H plus concentration measures how much free H plus is in the solution, sort of the acid part of the solution, while the OH minus is how much OH minus is flowing around, and that's the base part of the solution. And also remember that they do run opposites of each other. So if we do increase the H plus, we would see the concentration of OH minus go down and vice versa. So as one goes up, the other goes down, is the relationship that we do see between those two. Any questions on KW or anything like that? Yeah. And let's talk about the pH scale. The pH scale is a measure of acidity, and the pH scale runs from 0 to 7 to 14, and above 7 to 14 is basic, below 7 to 0 is acidic, and really 7 there on the nose is neutral. And really 7 is sort of your midpoint. So as you go from 7 towards 0, you're becoming more acidic. And as you go from 7 towards 14, you're becoming more basic as you head in that direction. To calculate the pH, it is this equation right here. That negative is just from PowerPoint. It's not really negative. But the pH is equal to minus the log of the H plus concentration. Or again, you can substitute in there if you like, minus the log of the H3O plus concentration. So again, they're basically the same thing. Now, this formula and every other one after this point, depending on your calculator as to which way you should properly punch it in. If you have a display calculator, so if you got a display calculator, you would punch in the negative button, the log button, and then the concentration using your exponent. If you have a non-display calculator with this formula and everyone else afterwards, you pretty much need to start with the concentration or the number. You then need to hit the log button, and then you need to hit the negative button. So depending on sort of which way your calculator works, you're either going to punch it in exactly like this, or you'll go opposite and punch it in backwards. If you're not sure if you have a display calculator or not, all you have to do is hit log. And if your calculator says log, congratulations, you have a display calculator. If you hit log and your calculator says error, congratulations, you have a non-display calculator. So that's how you determine that pretty easily. So with this one and all the other ones, you know, if you have a non-display, you usually got to kind of work with the number and go backwards. And if you have a display one, you basically push it in exactly the way the formula is sort of written. All right, so that's usually the important part there. All right, so let's talk a little bit about significant figures and pH. The number of decimal places that your pH value should have should be equal to the number of significant figures there are in the concentration unit. So just so we're clear, that is concentration sig figs to pH or pH-like value decimal places. So sig figs to decimal places, and vice versa. If you're going backwards, decimal places to sig figs. So why don't we try one, make sure everybody's calculator works. Once again, this is not negative, just from PowerPoint. If we have an H plus concentration of 1 times 10 to the minus 5, what is the pH to the right number of sig figs? So once again, if you have a display calculator, negative log 1 times 10 to the minus 5, non-display calculator 1 times 10 to the minus 5, log button and negative button. All right, so pH here will equal minus the log of 1 times 10 to the minus 5, which means when you put it into your calculator, you should get a pH of 5. Yes. So the proper recording of this is that a pH of 5, is it a 5.0, 5.00, 5.00000? That one feels like a lot to begin with. So I'm just going to take that one out of the running here. Which way should be the proper way to give this answer? So the rule is the number of significant figures in the concentration. So this is the concentration. How many sig figs does this guy have? It has 2 sig figs, right? So any number written in scientific notation, all the number before the times 10 part are significant. That means when we go to our pH, we are looking for not 2 significant figures. We're looking for 2 decimal places. Yes. So sig figs, 2 decimal places is what we are looking for there. Question on that there. So 2 sig figs, 2 decimal places. By the way, we're going to talk about going backwards as well from pH back to concentration. You do the same thing. Our main decimal places is how many sig figs your kind of concentration should have. Any questions on that there? By the way, this would be acidic, basic, or neutral. This would be acidic. It's less than 7, so it would be acidic when you look at the pH. Any question on that there? All right, so let's try some here. All right, so for each of these individually, 2 different solutions for number 1 and number 2. What is the pH in each case, and is it acidic, basic, or neutral? So take a couple moments here. You calculate the pH of that solution and the pH. Okay, starting with number 1 here. We're going to calculate the pH, which again is equal to minus the log of the H plus concentration, minus the log here of 2.1 times 10 to the minus 5. Again, negative log in the number, our number log negative. So negative log and 2.1 exponent butts in negative 5. Going to give us a pH here of 4.68 in terms of our pH. Once again, in terms of final answer, we got 2 sig figs, we got 2 decimal places in this case, and that is what we are looking for. This is again below 7, which means this solution should be acidic. Yeah. Any questions on that one there? All right, so for number 2 here, we are not given the H plus here. So remember that pH actually tells you what you need. You need the H plus concentration, not the OH minus concentration. So at this point, you could use Kw to get to the H plus concentration, which would be 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8, giving you we'll call it 1.7 times 10 to the minus 7 molar. Now that we do have the H plus concentration, we can put it into our pH, which is minus the log of the H plus. Gets you minus the log of 1.7 times 10 to the minus 7. Little log action there. 6.77. Which means this guy is slightly acidic, this guy. So remember, we're going to go with 7 on the nose is neutral. Anything above it will be slightly basic. Anything below 7 will be slightly acidic in this case. Now, if you plugged it into the equation, and you put this number in, not realizing that was the OH minus concentration. You obviously, as we just talked about, did not calculate the pH of the solution. The kind of good news is you did calculate something. Yeah, so this is the OH minus concentration, which means you actually calculated what is known as the POH, which is not the pH. It runs opposite of the pH, by the way. And that's not necessarily a bad thing because there's a nice relationship that the pH plus the pOH is equal to 14. So you could have took then the pH would have been 14 minus 7.23, and you would get back here to the pH in that case. You want to see that super slow motion again? All right. So you calculated what is known as the pOH, hence the name here. The relationship, actually, a nice one is if you take the pH plus the pOH and add them together, it equals 14, which means since you calculated the pOH here, which is this number, you take 14 minus the pOH, it actually will give you the pH in this case. So you're just like 2 slides ahead if you did that. But wrong for this question, but 2 slides ahead for the next one. So sometimes it's a nice convenient way. You maybe don't need to use KW as you just saw there. You could actually calculate with the pOH and then subtract 14 and get to the pH, and it makes it maybe a little quicker way to kind of get to the answer. But again, the correct answer here should be 6.77 for the pH. All right. So let's talk a little bit about that there. That's what the one we just calculated. So the pH scale changes basically pH of 1 unit by every power of 10 that changes. So 1 times 10 to the minus 3 has a pH of 3. 1 times 10 to the minus 4 is a pH of 4, and 1 times 10 to the minus 5 is a pH of 5. So every kind of power of 10 that you change in terms of the concentration, the pH will change by basically a unit. And as the amount of H plus increases, once again, that means the amount of OH minus decreases. That pretty much means you got a bunch of H pluses, more H pluses floating around. Then you do OH minuses. It is definitely going to be acidic in this case. It becomes more and more acidic the more H plus that you have basically floating around in that solution. So a couple different ways you can measure pH, which you might have done. This is a pH meter, and you calibrate it. And basically, it works off of voltages. You get certain voltages when you put the meter in and tell it this is a pH of 7, this is a pH of 4. Nice thing about pH meters, frankly, you stick it in and it tells you a number, which is kind of nice. Other ways you could get to pH is to use pH paper. And pH paper, if you ever maybe did anything with a pool, they have pool test strips and stuff like that you could kind of put in the water. And basically what you do is you dip it into the solution. The little boxes change colors. You kind of line it up to the key and go, kind of looks like a 7 or 4 pH, give or take. Obviously, this is a much more accurate way of doing it. Other ways in terms of acidic and basic that we talked about, again, doesn't give you the exact pH, but you could use litmus paper. And if litmus paper typically turns red, it means it's acidic. Again, will not tell you the pH. And if litmus paper turns blue, it means it's basic. Once again, will not tell you the pH, but will tell you whether or not the solution is acidic or basic. Yeah. It's it is LIT litmus. I know that looks just like what I wrote again. Let me try it one more time. It's actually a US there. I know my hand. I know. I'm sorry. So it's litmus paper, US at the end there. All right. So this is the pH scale, and again, as we talked about, 7 is neutral, and anything above it there, heading towards 14, is going to be basic. So that's sodium hydroxide, which is a strong base. Going below it towards 0, hydrochloric acid is down there, which is a strong acid. Here's some acids like vinegar, acetic acid, lemon juice, ammonia, which is a cleaner, is basic. If you have pure water, have a pH of 7, but oddly, if you take just water that's maybe not pure water, hasn't been filtered very well, or has been sitting out for a while on your bench, the pH of water will be acidic. Yeah, it'll actually be more acidic. And that's because the water will pick up some CO2 from the air. It will make some carbonic acid, which will increase the H plus concentration and bring the pH down. So sometimes people are surprised to see a pH meter, stick it into some water, it's been sitting out for a while. It's actually in the, 5-ish range or so in terms of the pH. That's why if you ever do anything with water and you really need sort of neutral water, a lot of times what people do is they boil the water. And when you boil the water, you remove the CO2, and that brings the pH back up to kind of a neutral thing, which is sometimes what people will do to kind of get a neutral for water. All right, so similar scales to pH, as some of you calculated a second ago, is the POH, which is, as we just saw, can be very useful. So the POH, once again, you need the OH minus concentration. And then the relationship between the two is that the pH plus the POH equals 14. It does give you, again, a variety of ways. You can maybe solve these guys, putting in our other formulas here, our minus log of the H plus for the pH, also our KW, which is our H plus OH minus equals 1 times 10 to the minus 14. So again, you may not have to use KW at all, but you can use KW if you want, and you'll get the same answer. So it's just really your preference, which route you want to take. One really, really important thing is, let us talk about one more time here, the pH scale, which is 0 to 7 to 14, the pH scale. And once again, this is acidic, that is basic, and 7 there is neutral. The POH scale runs opposite, which means 0, 7, 14. Below 7 is basic, above 7 is acidic, and 7 is still neutral on the POH scale. Most people in their head have the pH scale in their head when they're trying to determine, is it acidic, basic, or neutral? And that is the one you should always look at when you're trying to determine, is it acidic, basic, or neutral? Because when you're asked that question, one more time, is it acidic, basic, or neutral? There's how many answers to that question? There's actually only one answer to that question. Either the solution is acidic, basic, or neutral. What very common people will do is they'll calculate the pH and go, cool, it's above 7, so it's basic. Then they'll calculate the POH. And they'll go like, hey, it's like below 7, it's acidic. So the same solution is acidic and basic, which cannot be, yes. So it cannot be both. It only could be one. You should always look at the pH when you're doing that. And in this case, it should be basic is the solution. So it's a very common mistake people make. They calculate both, look at both numbers, give both answers. I will say, I don't think I've had anybody give all three, like acidic, basic, and neutral at the same time, but they cannot be both. So you got to choose just one. Always look at the pH to make that determination, because in everybody's head, this is pretty much the scale that you have in most people's head. And again, the POH does run opposite of the pH scale. Any questions on that? While we're here, let's talk about a couple other sort of calculations, maybe. So if we have the pH given to us, we could calculate the H plus concentration directly from it. So if you're given the actual pH value, you could actually calculate the H plus concentration. The H plus concentration will equal the inverse log of the minus pH. Now, on most people's calculators, when you do the inverse log, most people's calculators put a 10 and a caret. Then you want to do negative of the pH. How do you get to inverse log? Well, in most people's calculators, upper left corner, there's a second button. There might be a shift button up there, one of those two buttons. Then on most people's calculators, you have a log button, and above it is 10 to the x, which a lot of people have been using for scientific notation. You do not want to do that. This is actually what you're going to use this button for. So you hit the second or the shift and the log. It typically will put up a 10 and a caret on your calculator. And then you want to make sure it is not the subtract button, that you do the negative button and the pH at that point. So that is the way you would punch it in. If you have a display calculator, you have a non-display calculator, you would start with the pH value. You would then make it negative. You then would hit the second or shift button and then the log button, and that would give you your answer. So non-display, this is how you punch that in. display calculator, this is how you would punch that in. Any questions on that there? We could also do the same calculation for POH. From the POH, we could get the OH minus concentration, and that would be the exact same calculation, the inverse log of the negative POH. Once again, on most people's calculator, that will put a 10 and a caret, and you want to do negative POH. You would punch it in exactly the same way as above, depending obviously on which one you have to do. So all those things do give you a variety of ways you can solve these problems. Again, adding in the stuff we talked about in last there, minus the log of the H plus, our POH minus the log of the OH minus, our pH plus the POH equals 14. And once again, our KW H plus OH minus equals 1 times 10 to the minus 14. So all those things here, along with this and this, gives you, again, like I said, a variety of pathways you can solve the problem depending on what's given to you. There is no wrong way to do it if you choose a legitimate sort of way to go. They all should really, within rounding, get you pretty much the same answer, no matter sort of which way you go. So whichever way you're comfortable with, you know, you could kind of roll that way. You may be limited based on what they give you as to where you got to kind of start, but once you start it, if you're asked to calculate a lot of stuff, you could kind of go off in some different directions, and they all should get you to the same answer. Any questions on those there? All right, let's try our calculators here, see how they work, maybe. All right, let us do this one here. And then for each of these solutions, 2 separate solutions, let us calculate everything to make sure. So let's calculate the pH for this guy, the first one. Let's calculate the POH. And then let's also calculate the OH minus concentration. And is it acidic, basic, or neutral? And for the second one, let's do the same thing, pH, POH, H plus, and is it acidic, basic, or neutral? For things, we could get the pH by just putting it right into the pH equation. We could, if you wanted to, also use KW to get the OH minus concentration like we did before. So for me, I'm just going to actually go into the pH here to start with, since I could calculate that directly. So that's going to be minus the log of 3.6 times 10 to the minus 9. When I do that, minus the log 3.6 to the minus 9 gets you a pH of 8.44. Any questions on that calculation there? Again, at this point, I do have a couple of options. I could still go with the KW and get the OH minus. I could also, now that I have the pH, I could simply just subtract 14 from it to get to the POH, using the relationship that the pH plus the POH equals 14. That means that the POH would equal 14 minus the pH, which would be 14 minus 8.44. That would then give us a POH of 556. Any questions on those two so far? At this point, I still have multiple options to get to the OH minus. So since it's sort of a newer calculation, I am going to take the POH that I just calculated, and I'm going to calculate the OH minus by taking, once again, the inverse log of the minus POH. So again, when you punch that in properly on your calculator, you'll have probably a 10 and a caret. You want to hit the negative 5.56 and hit equals. And if you do that, you will end up with 2.8 times 10 to the 1, 2, 3, 4, 5, 6 minus 6 molar. Once again, to punch this into your calculator, if you have a display calculator, second or shift button, log button, negative button, 5.56 and equals. Yeah. If you have a non-display calculator, then you would go 5.56, make it negative, and then hit the second button, or shift button, and the log button. Yeah. So again, display, non-display way of punching that in. Once again, if you don't want to do it that way, you could still use that the OH minus concentration equals 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 9. And once again, you should end up with the exact same guy that we did above. And if you punch that in there, you get 2.5, which is not right. Try it again. Punch it in correctly would be better. Let's try that here. There we go. Gets you your 2.8 times 10 to the minus 6 smaller. So again, you can still use KW like we did before if you like that better, and you get the same answer. Any questions on how I got any of those, by the way? Also, by the way, you could have done KW up front, got the OH minus, and then went into the POH equation as well. To get to the POH as well. So again, that's an alternative pathway, should get you to the same spot. Any questions on any way there? This is going to be acidic, basic, or neutral, this one. We want to look always at the pH, and our pH value is above 7, which means this guy is going to be basic. Yeah. Any questions on any of those there? All right, let's do the same thing here for our second one. So once again, up front, you have two options. You could again use KW to get to H plus. You also could put this right into the POH equation as well. So that is what I'm going to do. I'm going to calculate the POH first. So here, the POH would equal minus the log of the OH minus concentration, which would be minus the log of 9.2 times 10 to the minus 2. That's going to give me minus the log 9.2 to the minus 2, 1.04 looks like. Now at this point, again, you have options, but to me, the easiest way to get to pH at this point is to use the same as we did to the left there. pH plus POH is equal to 14, which means in this case, the pH would be 14 minus the POH, which would be 14 minus 1.04, and that would get us 1296 in terms of our pH. Now, again, at this point, you could go the inverse log of the pH and get the H plus concentration. Once again, you could still use KW like we did earlier if you like that one better. So H plus could be 1 times 10 to the minus 14 divided by 9.2 times 10 to the minus 2. And that would get us looks like 1.1 times 10 to the minus 13 molar. Let's see here. The only thing we're missing is it acidic, basic, or neutral? And in this case, once again, we're going to look at the pH, which is this guy. And the pH here is 12.96, which is again above 7, which means this guy should be basic in this case. Yeah. Any questions on that there? So again, there's a variety of ways you could kind of work these depending on sort of your pathway, but they all should really get you kind of the same place. Again, with rounding, you might be slightly off on some of it, but it should be pretty close to each other, depending on where you round. Any questions on any of those there? All right, so the pH is 5.67. What is the POH? Why don't we also calculate the H plus and OH minus concentration? So take a moment there, see what you come up with here. Right off the bat by using the relationship, again, pH plus POH is equal to 14. That means here that the POH would be 14 minus the pH, which is 5.67. And that would get us 14 minus 5.67, 833 for our POH. Once again here, since we do have the pH given to us and the POH now, we can do the H plus concentration will equal the inverse log of the minus pH. Again, that is a 10 and a caret minus 5.67. And once again, that is your second log button there and negative that you want to put. So to do that there, second log negative 5.67 going to get us a H plus concentration of looks like 2.1 times 10 to the minus 8 molar. At this point, you could also use kW to get the OH minus concentration since you have the H plus, or again, you could do the same calculation here for the POH. And if we did the same calculation, basically OH minus would equal the inverse log of the minus POH. So that's going to be a 10 and a caret minus 8.33. So shift or second and log, negative 8.33 and equals 4.7 times 10 to the minus 9 molar in this case. Yeah. Any questions on any of those there? Yeah. Yeah. Okay. Let me try again here. So we did our shift or second log, puts a 10 and a caret, right? Negative 5.67. And yeah, that does say a 6. You see, that does say a 6 there. Thank you. I was just testing to make sure you knew how to do it. I'm just getting, no, I get an extra point for being old. All right, so that's 2.1 times 10 to the minus 6. The other one good on that then? Yeah, I hope. Yeah. All right. Sometimes it's dark over here. It's hard to see the number in the corner. You know, when you have it like right here to your face, it's really hard to see those numbers. Other questions on that? Thank you. All right, let's just try this one. We'll do what it says. So we're just looking for the H plus concentration here. So see what you come up with. We'll just do H plus here. Or H plus. So again, in this case, it will be H plus is equal to, again, basically 10 in our caret minus 3.14. Again, make sure you use your negative button, not your subtract button, and we will end up with, provided I can read that number, it is 7.2 times 10 to the minus 4. Looks like a winner, perhaps. By the way, we are going backwards here. So as we talked about earlier, just to remind you, pH has 2 decimal places. Concentration then will end up with 2 significant figures. So again, going backwards, that is how those guys relate to each other. Any questions on that one there? All right, so I think we'll skip this one here. So let's talk a little bit about the pH of a strong acid and sort of how it's a little bit maybe different than more of a generic sort of acid. So if we had a strong acid like HCl, it's a strong electrolyte, which means pretty much it will 100% when it's in solution, it will break apart into H plus and Cl minus. And in the case of pH, it really is the H plus concentration that is the most important to allow us to calculate really the pH of that solution. So if this concentration was 0.1 molar, we really want the H plus concentration to allow us to calculate the pH. Remember that with molarity, you could kind of do like stoichiometry. It is a 1-to-1 relationship between the HCl and the H plus, which means the concentration of the H plus would also be 0.1 molar. So that means that's really all we need to go into our pH, which would give us a pH in this case minus the log of 0.1 molar. Gives us a pH of 1.00, which obviously would be acidic, which we would expect since it's a strong acid. Remember some strong acids, as we talked about, I think earlier on in this chapter, hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, hydroiodic acid. So these are some strong acids. So really, if you're dealing with a strong acid or even really a strong base as well, you really just need to figure out what the H plus concentration is and what the OH minus concentration is to allow you to calculate the pH of that particular solution. So occasionally, you may not be given just a generic H plus or H3O plus or OH minus. You may actually be given a formula. For our purposes here, if you are given a formula, it should be a strong acid or a strong base, because the weak acid or weak base is a much longer calculation. So and we don't go over that in this class. So if you're given an actual formula of an acid or base, you could probably safely assume in this class that it is a strong acid or strong base. And pretty much in most cases, that will also be the concentration of the H plus or OH minus that you would need to calculate the pH or the POH. So for example, here, this is perchloric acid, which once again is a strong acid. So if we think about perchloric acid, it will break apart into H plus and ClO4 minus. Remember, in solution, this is 100% of what you got floating around, which means since this guy is 0.025 molar, this guy here will also be 0.025 molar. And really, once again, that is all you need to calculate the pH, which would be minus the log of 0.025. And that would get you a pH of 1.60, which again is acidic. Now, for example, if you had a base like sodium hydroxide, 0.025 molar sodium hydroxide. Sodium hydroxide is a strong base, which means it would break apart into a sodium ion and a hydroxide ion. In this particular case, we would be interested in the hydroxide concentration because that will allow us to calculate not the pH, but the POH, which will then allow us to get to the pH from it. So for example, here we could do the same thing. It's a 1-to-1 relationship between those two, which means the OH minus concentration would be 0.025. Once again, because this is the OH minus concentration, that would get you the POH, which would be this number, which should be the same one we just got there of 1.60. But that again is not the pH, that is the POH. So the pH can be found by taking 14 minus that number. Gets us a 1240 pH. And that makes a lot more sense because 1240 is basic, right? And sodium hydroxide is a base. So that will get you your pH for that base. So if you're given the formula of a strong base, you basically do the same thing. The only difference is you got to take it one more step because you'll be able to get the hydroxide concentration. You first got to get the POH and then subtract 14 to get to the pH. So because it's a base, you kind of have to take that extra step to get to the pH. Any questions on either of those there? A question on how to calculate pH, POH, H plus, OH minus, figure out if it's acidic, basic, or neutral. Yes. I'm sorry, say it one more time. To calculate like what we did right here, or like right here. Is that what you're asking? Yeah. Yeah, to calculate the pH or even the POH, which is basically the same calculation, For the pH, basically RPOH. On your calculator, if you have a display calculator, you would put in the negative button, the log button, and then either your H plus concentration or your OH minus concentration, using your exponent button. If you have a non-display calculator, you would start with either the H plus concentration or the OH minus concentration. Once again, using your exponent button, you then would hit the log, and then you would hit the negative button on your calculator. Yeah. And that would be how you would calculate either pH or POH. If you needed to calculate either H plus or OH minus from either the pH or the POH, you would do on a display calculator the second, the log, the negative button, and then the pH or POH. And on a non-display calculator, you would do actually the number first. So you would do the pH or POH, make it negative, then hit the second button, and then hit the log button. So that would be how you would do either of those there. Yeah. Good. Yeah. Other questions? All right. Then let's finish talking about in this chapter here buffers. So a buffer is a solution that will resist changes in pH, even if you add more acid or base to it. So a buffer is a solution that will resist changes in pH if you add acid or base to it. The first misconception a lot of people have about a buffer is it is a neutral solution, and it is not necessarily a neutral solution. You can make a buffer at any pH you like. You can make an acidic buffer, you can make a basic buffer, you could have a neutral buffer. So you can actually make the buffer any pH you like. The thing is, whatever pH it starts at, if you add acid or base to the buffer, additional acid or base to the buffer, the pH pretty much will stay around that number. It might go up a little bit, it might go down a little bit, but what you will not see is a big giant jump in pH. So, for example, if I made a buffer at a pH of 6 and I add acid to it, it will stay around a pH of 6. It might come down maybe 5.9 something or something like that, but it will not go from a pH of 6 all the way down to like a pH of 1 in a buffer solution. If I made that buffer of a pH 6 and added base to it, it would go up maybe a little bit. Maybe it goes to like 6.01, 6.1, something like that, but it will not go from 6 all the way up to like a pH of 12 by adding it. It's able to resist really big changes in pH when you add an acid or base to it. The reason it's able to do that is what makes up a buffer. A buffer has to be made up of a weak acid and its conjugate base, or a weak base and its conjugate acid. And sometimes referred to the salt of its conjugate base or the salt of its conjugate acid. They both actually have to be in the solution together to begin with. So you need both of those things in the solution in order for a buffer to work properly. A buffer can never, ever be made up of a strong acid or a strong base. So that is a no-go for buffers. So you cannot make a buffer out of a strong acid or strong base. The reason for that is a strong acid or strong base is a strong electrolyte, which means when you put it into solution, it breaks apart, which means there's no way to keep the acid part in the solution. There's no way to keep the base part in the solution. Now, a weak acid or weak base or weak electrolytes, if you remember, weak electrolytes pretty much stay together, right? But break apart a little bit. So because they're weak electrolytes, what that allows you to have in the solution is some acid there and some base part of the buffer there. So it's able to keep it in solution because they're actually weak electrolytes. They won't 100% break apart. So how does a buffer really work? Let's talk about really how a buffer really works. So for example, let's talk about a non-buffer situation. In a non-buffer like our good friend water, which is not a buffer. If I add a strong acid like hydrochloric acid to water, what's going to happen when I do that is it will 100% break apart into H plus and Cl minus. Which means in my solution here, when I add that to water and I add my HCl in there, I pretty much just created a lot of H pluses really, really quickly. Yes. What happens when the concentration of H plus increases? What happens to the pH? It goes down. Yeah. Greater amount of H plus, less OH minus. You're going to see a really big jump in the pH because you just added a bunch of H plus to the solution. That's basically what pH is, right? When you calculate the pH, it is minus the log of the H plus concentration. So the more H plus you have free in the solution, the more acidic it's going to become. And you're going to see, for example, if we had pure water at pH of 7, it will go from X7 down to 2. Really big jump in pH because you introduced a lot of H plus really, really quickly. Any questions on that? Now, what would happen if we added sodium hydroxide to our non-buffer, which is our water? It also would 100% break apart into sodium ion and hydroxide ion. Now, if we look at our beaker here of water and we add our sodium hydroxide to it, we're going to get a bunch of sodium ions and we're going to get a bunch of hydroxide ions, really. And we just added a lot of free hydroxide. And if you remember, as the hydroxide concentration increases, the H plus concentration goes down and the pH goes up. So in this case, where water is not a buffer, by adding the base to it, you have all this free OH minus floating around, which is going to cause the H plus concentration to come way down, OH minus concentration to come way up. And the result of that is it's going to become very, very basic at this point because you have a lot of OH minus floating around in the solution. So again, if we start at a pH of 7, it will jump up maybe to a pH of 12, 13, something like that. A really big jump in pH because we just created a bunch of free OH minuses very, very quickly. So this is what happens when you put a strong acid or strong base into a non-buffer solution. Because it creates a lot of H plus really quickly, you get a really big jump in pH. And when you create a lot of OH minus really quickly, you also get a really big jump in pH. So why does this not happen when we add it to a buffer? So let's take a look at adding these exact same things to a buffer situation. Let's use the HF, which is a weak acid, and sodium fluoride, which is its conjugate base. So this is a weak acid and its conjugate base. And if you can't see the conjugate base, the sodium is not really doing anything. It's really F minus, which is its conjugate base that's happening here. So when we make a solution of this, which is a buffer, what's going to happen is in this buffer, we will get the HF, which will actually set up an equilibrium, and we will have both of these guys in the buffer to begin with. We will have the acid part of the buffer, really, and this is really the base part of the buffer, the F minus. So now when we take the exact same acid and we decide to add it to this buffer, so if we take hydrochloric acid, it is actually going to do a reaction because both of these things are in there in pretty good quantities. The acid is going to react with the base part of the buffer, right? They're acid-base reactions. So that's what's going to happen. When we add hydrochloric acid, the sodium fluoride will react with it and it will do a double displacement reaction. We will go like this and we will make this basically. That's a positive, negative, guys. So we're going to switch partners. And the result of that is we will make HF and sodium chloride. So a little bit different what happens here when we add the hydrochloric acid to this buffer. We made HF, which was part of the buffer to begin with. So that's not going to screw up the pH. We actually made part of the buffer that we used. Sodium chloride is a neutral salt, so it's not going to mess up the pH, but it is actually what we do not see here that we did see on the previous one. What did we see on the previous one happen when we added acid to water? We saw a big amount of H plus being formed. When we added it to the buffer, no more free H plus was formed. And because there's no more free H plus that was formed, the concentration of H plus stays relatively constant. And if the concentration of H plus stays relatively constant, that means the pH will also stay relatively constant as well. So the amount of H plus that was there at the beginning, as you can see here, there's a little bit of H plus there to start with, basically stays the same. We didn't add any more free H plus. And because we really didn't add any more free H plus, whatever the pH is, it pretty much will hang out right about there. Will it go down a little bit in this case? It will. You add a little bit of H plus, so it will come down a little bit, but you will not see a really big jump in pH. So it'll come down just a little, but you won't see it again drop from like 7 to 2 or anything like that. Again, maybe it starts at 7, drops to like 6.9, so very close to where it started at. Question on that there. Now, if we added sodium hydroxide to this same buffer, the sodium hydroxide, which is a base, will then actually react with the acid part of the buffer. And it also will do a double displacement reaction, basically an acid-base reaction. And we will get NaF and water formed. So once again, as you can see, we actually create part of the buffer by using this reaction. That's not going to affect the pH. We are also making water here, which will not affect the pH. It is once again what we do not see here, which is we do not see any free OH minus like we saw when we added it to water. And because OH minus concentration stays relatively constant, the H plus concentration, which is tied to it, remember they go opposites of each other, right? So as one moves, the other moves. The H plus concentration then will stay relatively constant, and that means that our pH will stay relatively constant. So the reason why a buffer can resist changes in pH is because it has an acid part, it has a base part. So when you add additional acid or additional base in there, what it's able to do is actually prevent the formation of free H plus when you add acid, prevent the formation of free OH minus when you add base. What those both are going to do is basically keep the H plus concentration where it was at to start with. And because that concentration doesn't move, basically the pH doesn't go crazy and have big jumps. So it's able to remain relatively constant. Question on that there. So just a graphical representation here. If we had a buffer and we have an acid part and we have a base part of the buffer, when we add additional acid to the buffer, it will use up some of the base part, but it will make some of the acid part. So you'll make some more acid part, but use up a little bit of the base part. And when you add more acid or add more base, you will make some more of the base part, exaggeratedly drawn here, and you'll use up a little bit of the acid part of the buffer. There is a limit to how good a buffer will work. What happens if I just keep adding acid? What will I eventually chew up? If I just keep adding acid, it's going to continue to react with the base part, right? Until there is no more base, which means at that point, it no longer will be able to function as a buffer. And if you keep adding acid, you're now going to be adding a bunch of H plus. And at that point, you will see a big jump in pH that will occur. So there is a limit to how good a buffer could be, and there is what is referred to as a buffer capacity. But that is why a buffer has to be made up of a weak acid or weak base combination, because that allows the buffer to keep both of those things in the solution at the very beginning, the acid part and the base part, and that's essential to how a buffer can work. So a couple of combinations, HF, like sodium fluoride, acetic acid, and sodium acetate are buffers. Anything that's a weak acid or a weak base, ammonia and ammonium chloride, these are all examples of buffers. Hydrogen carbonate and carbonate, also buffer systems like in your blood, right, to keep everything working really well. Any question on buffers? So again, the biggest misconception is people do think that they are always neutral solutions, but they're not. It's just whatever pH is made at, it's able to basically maintain that pH. Any questions on that there? Yeah. Yeah, those are common buffers, I would say. Yeah. And then I think in your book, it talks about the carbonate and hydrogen carbonate one, bicarbonate one is, and also another common one as well. Other questions?